there is very, very interesting things happening. And we have today two speakers that will report about the Rosetta mission. Why two? It's quite easy. We have two major parts in the Rosetta mission. One is the actual orbiter. It's a spacecraft about as big as a small car with 32 meters wingspan. And it carries a small payload, which is called Philae, and which will be detached and land on the Comet very soon. So we have one speaker who will inform you about the Rosetta orbiter mission and one speaker who will talk about the Philae lander. The first speaker will be Dr. Gerhart Schwein. He is the first planetary scientist that ESA ever employed in 1985. He was the deputy project scientist for the Giotto mission, the earlier mission to Comet Halley in 1986. And since 1985, he was the project scientist for Rosetta. Then he turned into the Rosetta mission manager after the launch in 2004. He actually retired in March of this year, but you will not feel much of retirement when you hear him speaking. He kept all the lines going, and he keeps following very, very closely and active the mission. He will talk about the Rosetta orbiter, and he will be followed by Professor Jean-Pierre Bibring. He is an astrophysicist at the University of Paris in Orsay and at the Institut d'Astrophysique Spatiale, also in Orsay. He is what we call the lead scientist for Philae. He is also a principal investigator for one of the major instruments on the Philae lander, namely the Shiva cameras. He is also co-investigator of several other experiments, both on the lander and on the orbiter. He is also active in Mars Express. He was active in Cassini-Huygens and in the Mars Reconnaissance Orbiter. So he is somebody who is very familiar in space. Let me call Gerhart Schwein to give you the first presentation on the Rosetta lander.
Thank you, Ben, for the nice introduction and also telling everybody how old I am. But I still feel fairly fresh, as you said. And ladies and gentlemen, I will give you an overview of the Rosetta mission, basically the orbiter, and then Jean-Pierre will give you more details on the lander and also more details on the result we have achieved so far. And it's unfortunate time where we cannot show all the results because our dear colleagues in the instrument teams are very busy to prepare their first papers, and for scientists it's really very important to have refereed papers on his CV, and therefore we're in a time where a lot of things happening, but we can show you, I believe, quite some exciting results. And this is what we saw end of July. This was, so to say, the wow factor to see for the first time a resolved image of our target nucleus. It's the first impression by a lot of people was that this is a rubber duck in space. It looks really great, and it's a fascinating object. You see, it's not something that's like a sphere or close to a sphere, but we really realized right from the beginning that we are in for a wonderful science mission. And I will go back a little bit, and I think that's also important for a lot of people who work in exploration, work in planetary science, that it takes quite some stamina to really get a mission like Rosetta going. And everything basically started in '84 when the then director of science in ESA came up with the idea to have a long-term program to provide opportunities for the European science community to also embark in very complex missions, not only in planetary science, but also in astronomy and in solar physics. And that was the Horizon 2000. But it basically also shows you that you have to have the right people at the right time with the right ideas. And I could give you a long lecture on cometary missions that never came about. The ideas go back in the 70s of the last century, but with this Horizon 2000, ESA could grab the opportunity. And I only gave a few names, as I said, Roger Bonnet, our then director, and having this long-term program where you could get planetary cornerstone missions, basically flagships, this idea was picked up by Professor Johannes Geis and Professor Hugo Festig, who really jumped on it and said, we need a mission to a primitive body, hopefully with the same return. And it was in the right time because ESA and NASA studied in the primitive body science study groups. They studied mission scenarios, and when ESA decided to embark what was originally a Comet nuclear sample return, then this group just ceased to work. They said, this is what we wanted, and we got the support. Why do we want to study comets? And I just go here briefly through the history of the solar system material. You know, when we had the Big Bang 13 billion years ago, only hydrogen and helium were produced, but then from the hydrogen to the heavy elements through the stars, these were produced. Then we got from the heavier elements through the dust in supernova explosions and other really violent processes in stars. And in the end, we had the complex molecules in the dark clouds in space. This is a very, very short introduction to how this material is created, but it's important that we went from the dust to the more complex molecules in these dark clouds. And basically this material, this is what we found in the pre-solar nebula. The pre-solar nebula was this cloud of dust and gas out of which the planets formed. And this long evolution over 4.6 billion years ended up in what we see in the right corner below, our solar system, our planets, the whole diversity of these planets. Now the question is, how came this about? And the only objects that have the material that was in the pre-solar nebula are the comets. They are so small, they were far away from the sun, not heated up too much. Their own gravity was so small that there were no inner processes, and they preserved the information from the pre-solar nebula. You know, the Earth and other planets, they changed. There we can't go back. And this is exactly what we want to do when we study comets. We want to go back to the infant state of our solar system, to the pre-solar nebula, to learn about the condition, to learn about the material out of which the planets formed. And therefore, the only objects that are accessible to us are the comets. And that's basically behind of it, that we do archaeology in space on a much longer time scale than we do on Earth, because we do it on the time scale of billions of years. We go back 4.6 billion years. Here, you just give an explanation of the names of the mission. We have Rosetta, the orbiter spacecraft. We have Philae, the lander. That all goes back to the Rosetta Stone that most of you know, which helped to decipher the hieroglyphs. And it was not only the Rosetta Stone that was used by Champollion to do it, it was also an obelisk that was found in the Philae temple of Isis. And we thought already in the beginning that Rosetta would be a great name for this mission. And one has to be careful. Rosetta Stones you have everywhere in science. But I think what we will demonstrate, not today, but over the next couple of years, is when the results are analyzed, is that really the Rosetta mission is a Rosetta Stone in planetary science. By the way, all the obelisk and the Rosetta Stone are all nicely preserved in the UK. So if you go to the British Museum, you will see the Rosetta Stone, and then you have to travel in South England, and you will see the obelisk there. Just briefly, the primary science goals that come out of this question that we want to look back into the infancy of the solar system is, first of all, if we study an object, we have to see how that object works, and therefore we will follow the comet over a long time and then study how the comet processes work. We have observed comets from ground-based observations. We know a lot, but we don't know the details of the way they work. We look at the origin of the comets, and we want to take a complete inventory of the comet's composition, about the molecules and the grains and the physical properties of the comet. And as I said, we want to understand the role that comets played in the evolution of the planets, because the planets accreted out of objects that were of the size of a comet. The other question that goes a little bit beyond that is the role comets played in the evolution of the Earth, because 3.8 billion years ago we had the heavy bombardment, and it's quite sure that a lot of cometary material impacted on the Earth, and there was, or still, the question if part of the water we have on Earth in the oceans came by comets. And last but not least, and this is something that is really, perhaps really interesting everybody, is how did life evolve on Earth? And comets didn't bring life to Earth, but comets brought very complex molecules. Comets might have played a very important role in the way that life could have evolved, bringing these complex molecules to Earth. And we know that we have amino acids in meteorites. We have also found amino acids in one of the grains that Stardust mission from the US brought back. When we designed this mission, and that was 20 years ago, where we really started to build the hardware in 93, the only thing we knew about comets were the ground-based observations, and what you see over there, this is an approach movie, which is a sequence of observations or images that were taken by the Halley multicolor camera. That was the only thing we knew about comets from close by. Halley in '86, 30 years ago, was the first mission that demonstrated there was a solid comet nucleus. The next mission after that was only in 2001, Borrelly with Deep Space One, and then you had a sequence of other flyby missions. That was all what we had from close measurements from comets. And what we do now, which is a big first, is Rosetta, to rendezvous with the comet, to stay with the comet, and study it for at least 1.5 years. When we started in '85, we wanted, as I said, we wanted to have a sample return. So we wanted to have a comet nucleus sample return together with NASA. For programmatic reasons, that could not be done. So we had to go on our own. And in 1993, we then got the approval for the Comet Rendezvous mission, including 2 asteroids flybys. And that is the mission we have today, Rosetta. And the slogan we coined at that time was, we could not bring comet material into our laboratories, and therefore we bring a laboratory to the comet. And I think that's very important that we try to do it, to have a mission that is not only focusing on 1 or 2 aspects in cometary science, but we wanted to have a very broad approach to cometary science, fly a lot of instruments, and what we then finally got is also a lander that we could transfer to the comet, thanks to the to DLR, the Max Planck Institute in Kattenburg-Lindau, and CNES. Just briefly about the spacecraft, Ben mentioned already, is so to say a 2 by 2 by 3 meter big. It's like a big fridge, as you have it in the States. What is very important in the spacecraft is that we have these solar arrays, huge solar arrays, because we have to go far away from the sun. We have to go close to Jupiter's orbit. And as we don't have RTGs in Europe, we have to do it with solar arrays. And that was one of the enabling technologies we had to develop, the so-called low-intensity, low-temperature solar arrays. The launch mass of the spacecraft was just over 3 tons, and more than half of it was fuel. And in the meantime, all the fuel, or more or less everything, has been burned. There's a couple of kilograms left, more than enough that we need for the operations at the Comet. And also one of the very important things that for such a mission, when you go to a comet or we go to outer planets, is that the real science comes at the end. You have a long flight time, therefore you need a spacecraft that's really built to last, in our case, 12 or plus years. Here is a closer look on the spacecraft. It's a huge solar array, 32 meters tip to tip. And what is important is that all the instruments are fixed body mounted basically on the upper platform, and you have a few booms out there. That is for our dear friends from plasma physics. They have to stay away a little bit from the spacecraft body, but all the other instruments are on the top, so if somebody wants to look in a certain direction, everybody has to look the same direction to take his or her measurements, and that is a little bit of complication sometimes for the science operations. We have, and as I said, we wanted to have a very wide range of instruments, and I just go through it. We have for the remote sensing to really get a good image of the nucleus. We have OSIRIS, which is a narrow-angle, wide-angle camera. We have ALICE, a UV spectrometer. VIRTIS is a visual and infrared mapping spectrometer. And we have a microwave spectrometer, MIRO, that was provided by the US. Then we have the instrument, very important to study the composition of the nucleus. Rosina, it's a neutral gas and ion mass spectrometer. It's actually 2 big mass spectrometers, time of flight, and a double focusing, plus a sensor that measures the ambient gas pressure. We have the dust mass spectrometer, COSIMA, and we have an atomic force microscope that will give us the structure of the dust grains with a very high resolution in the nanometer range. And then we also have some instruments that basically describe the environment, the dust environment with GIATA, the plasma consortium, which is actually 5 sensors, and we have the radio science instrument, and one instrument that is both on the orbiter and the lander, that's CONSERT. That's some kind of tomography. It's really, so to say, looking through the nucleus and provides us with some information if the nucleus is on a large scale homogeneous or inhomogeneous, which is quite important to learn that, to see how the nucleus greeted. I just come now to some of the results. This was basically after the wake up, after the long 31 months hibernation, the first image of the comet taken from 5 million kilometers, just showing that the comet was still there, and secondly also to demonstrate that the camera was working. Then this was enabled. Then we really came close after a sequence of orbit maneuvers, the second deep space maneuver, which was a sequence of maneuvers over a couple of weeks. We were close, and this is basically the first high-resolution image out of a distance of nearly 2,000 kilometers. Here the pixel resolution is 37 meters, and that is taken by the OSIRIS narrow-angle camera. And you see the pixel resolution here, this 37 meters. This is close to the best resolution we had so far from the other flyby missions. Yeah, the resolution we had before was just below 30 meters. So you have to see that already in the first time we got this wonderful image that showed a lot of details. And this was the image when we entered into orbit on the 6th of August. A couple of weeks ago, that was the first orbit was at a distance of 100 kilometers, and this has a resolution of just below 6 meters. And you see, this is really a fascinating surface. You see you see cliffs, you nearly see everything. You have the neck region. It's really wonderful and impressive. And the last couple of weeks were really devoted, especially by our lander team and our colleagues in ESOC from the flight dynamics team, really to look that we can find a landing site. And Jean-Pierre will go in that as well. From the other instruments, I can't show too many results, but one thing is really convincing is also that COSIMA, the dust mass spectrometer, at least has collected one grain that you see here. You see the target before and after, so there is dust grains have been collected, and I believe also the spectrum has been taken, so there is also great science there. This, I don't know if you can see it on the screen, this shows, so this is the first little bit enhancement and shows activity in the neck region, and the comet is active, we know. Miro has measured right from the beginning how much water is lost. It was, so to say, 2 glasses of water in the beginning per second. Now it's much more, and it's increasing because the comet gets closer to the sun, and then activity as it warms up will increase. But these are the things that we will see over the next couple of months increase, and it will be really, everybody's looking forward to see how this surface changes now when the activity goes on. This is something spectra from the magnetometer that I got from Professor Glasmayer, and they already found that there are some peculiar types of waves that have not been seen before, but they can nicely model this, and it's really for them one of the first results which is, so to say, interesting in the sense that we didn't expect these things to come, and if you want to have more information on this one, Professor Glasmayer is in the room and he can tell you all about it, but he's also one of the scientists who assures us that this is great mission, great science, and they are just looking forward to have much more data to come. And this is one of the recent images taken by the NAVCAM. This is our ESA's navigation camera on board, which gives us really tremendous good images as well, and that just shows you what object we have here. And one could go on and try to interpret these things already. We will learn much more when we get even closer, and we just reached, I think a couple of days ago, we went down to 30 or 20 kilometers. Yeah, to 20 kilometers, so you see this will give much better pictures, and then together with a narrow angle camera and this close distance, we will get down to a resolution of a couple of perhaps 10 centimeters now, and I think the closer we go, we will see much more details and perhaps also more things to scratch our head. And I will close with this one and hand over to Jean-Pierre, who gives you much more results and also an introduction to the viele Länder. Thank you.
Mesdames, Messieurs, dear friends, colleagues, thanks a lot for being here to share with us something which I consider maybe the most historical mission that we'll really be together in. At least for space exploration of the solar system. It's absolutely amazing to consider that exactly 6 weeks ahead of us we'll land on the comet. And what I would like rapidly is to tell you where we are, what we have learned already, and what are the expectations on that, and why really we are so excited there. So that's essentially to give you my email address in case you would like to correspond afterwards, because we have only a few minutes here. And importantly, of course, that none of this would have been possible without the help of first Herman, which is the other lead scientist of this venture. We have 10 PIs on the orbiter and 10 PIs on the lander itself. So it's really a great number of teams that we have here together. So again, things go very, very fast. This was exactly July 12th. For the first time, we understood that the body was really very different from what we might have expected, and nothing really resembled what we thought might be a cometary nucleus. And rapidly, we had this movie, which of course is well known now, that when we saw that, we said, well, really, the comet is not cooperating, its behavior. I mean, how can we just land on that? It's tremendously, of course, it's an accelerated picture. It turns in 12 hours, but still, you know, it looks really more than bizarre. And rapidly, we got some much better images. And the humor went better because we understood that there might be a possibility to land there. And in a few weeks, we consider that although it's rotating rather fast and with these bimodal things, there might be possibilities. And actually, in 2 months, just 2 months after the first images, we're already capable, thanks to a lot of activity in different centers, to locate 5 and then 2 sites in which we would be able to land. And these are the famous site now, J and C, that I will go back to that now. And this will happen essentially in 6 weeks ahead of us. So it will be, there has been 2 months prior between the first observation of this double structure, the location of 2 landing sites, and then from this time to the final arrival, another 2 months. So it's really very, very fast. And of course, you can imagine that we have not really taken a lot of time now to make all the science with. As Gerhart said, it's a little frustrating maybe for you to realize that we are not even supposed to give any result because we have not a single science paper published yet. But of course, because we are just among ourselves here and no press, nothing, so we'll dare to say a few results, of course. But please understand that most of that has to be published, and it's not yet published. So I will, in a few minutes, tell you what I think are the highlights we learned and what we expect to learn afterwards. So what have we learned for the moment? First of all, we know the shape. It was not obvious and a very strange shape. We know the dimensions. Typically, it's a very small body, a little larger than most of the body that are the same sort of families. It's typically 4 kilometers in what I might call a diameter. It's not a diameter, it's, let's say, 4 kilometers aside. So from any part to the center of mass, you have 2 kilometers, and that gives you an idea of the sort of velocity we can get there and gravity. So rotation is 12.4 hours. It's well known now, and that's important. And the albedo is very low. Albedo is less than 5%, but we knew that already for quite a time because from remote, we knew that it was very dark. What is new is that we know that the albedo is the same, whatever the scale. In other words, there is no, what was really expected, patches of ices and patches of very dark material. The 5% we see, which is a little less than that actually, you know, it appears very bright in that sort of picture. It's just an enhancement of the dynamics. It's very, very dark. It's darker than this black material here. It's darker than coal. It's really very, very dark. And I will go back to that, of course, because that's fundamental. But what is important that we discovered that this darkness is really at all scale, down to the resolution of the camera we have. We have now a camera giving a resolution of less than a meter, actually half a meter, and we, at essentially every pixel we see, the albedos are identical. So it's almost covered by this dark material. I will go back to that, and that was not expected. The mass, we know, it doesn't tell you a lot, 10 to the 13 kilograms, but by comparison, it's 10 to the 12 times less than the Earth's mass. So it's very, very small. And density we know also, and the density is very, very low also. It's less than 0.5, it's 0.4 something. We don't know exactly yet because, again, we have not yet measured with sufficient accuracy the volume and the mass, but it's very close to that. In other words, we know, of course, it's made essentially of ice, but its ice is a very peculiar stage because if you have ice, compact ice, of course, it's much higher than that. So it's a very porous ice, and we hope it's not porous too much for us to be able to land, and it will not crack under the landing, but it's not even obvious. So we know the density, very low density, and the gravity also. The gravity is this, and again, for comparison, it's about 10 to the 12 times less than on the Earth. In other words, our 100 kilogram lander, when it arrives, will be less than the mass of a fly on the Earth. So we can really go wherever you are. The gravity will not really disturb the position of the lander there. So that's what we knew, and rapidly, over a few weeks, we discovered that. The next, which I will take a few minutes or a few seconds to discuss here, is the question of outgassing, because most of what we have really observed now has to do with the outgassing. Outgassing is well known, of course, because it's essentially made of ice. We don't know exactly the ratio of CO2 and H2O, but it's essentially H2O ice, as we see from outgassing, from all the comets, this one too. So we know the rate. It's not very active comet. It's just a standard comet with respect to that, although it started activation rather early on because we are still at more than 3 AU now, because we'll be at 3 AU in 6 weeks. But it started essentially outgassing CO, and then HCO is starting now. But what's importantly, and this was not really known, that the outgassing is not homogeneous over the entire body. And all the features that you see here, I will go back to that, has essentially to do with the outgassing effect. There is no craters in the sense that you are used to craters because most of the bodies in the solar system have suffered a huge or several huge processes with impacts. Comets have not, essentially, because they were formed much earlier to the heavy bombardment that we know happened, suffered all the asteroids did, and the planetary bodies did also. The comets no, because they've been probably ejected rather far from their orbit when they formed early on. So it's not craters. All the features you have essentially have to do with the outgassing. Again, this is essentially something that we will study more than we have studied, but that's important. I will show you a few things. So that's an enlargement, a splendid enlargement of this comet here as it is now. And when you take this picture with a huge stretching of the dynamics here, of course the colors are not true color here, it's just for you to see the thing. You see where the outgassing comes from essentially. The outgassing essentially has to do with the topography, and because it has to do with the topography, as soon as it starts from where, it amplifies the variation of the local topography, and it makes that sort of things that you see here. I have no pointer, but you see what I mean. So what we call the neck in between the two lobes has been essentially sculptured by the outgassing itself. And that's, okay, there is still people discussing that, and possibly it will be different, but now that we can do a lot of things like that, we see really where it comes from, and most of, not the entire, but most of the outgassing comes from this region between the two lobes, and that's essentially the reason why we have these two lobes probably now. So when now I take an image from this side, this is that splendid image here, when you see, as seen, so the neck in between is in between, exactly, and you see on the other side here, this big erosion cliff that we see over hundreds of meters. It's a huge cliff which has been essentially cleaned of the dust. The dust went elsewhere, so it's a bedrock, if I can say so there, bedrock and ice. And essentially erosion has been made by the outgassing here. We don't know when it started. It's probably very recent. In any case, it came when the outgassing started, which is only a few tenths of perihelion passes, so it's a few centuries, no more than that. But you might know that this comet had a modification of the trajectory by a perturbation of Jupiter a few tenths, a few decades, and it might be only recently that this erosion went very fast because it come now much closer to the sun than it used to be. So that's feasible. And of course, if you have the outgassing, most of the material is expelled. The ice goes into vapor in the coma itself. That's why you call that a comet. But the refractories, the most important grains, remain there and just essentially settle down and make like a regolith, in a sense, deposition, as you will see there. So you have deposition in many places on this comet here, and you have sort of a dichotomy between the cliffs without soil, essentially, and the deposition on terrace here. And here, for example, when you have an enlargement on the side, you see these bodies here. What are they made of? We don't know exactly yet, but as I will say in a few seconds, the composition of all what we see is identical, and identical to material which is essentially rich in organics. We do not see ice at all, although it's made of ice, and I will go back to that in a second. So you have a lot of these places here, and when you enlarge that, this is one of the best images that we obtained a few weeks ago by the OSIRIS camera on the orbiter. None of this is published yet. You can see that you have even boulders down to very small scales, which are very, very impressive, and that's fundamental because we consider that this part of these grains, as I show here, for example, might really be the equivalent, if not the real, bodies out of which the planetesimals grew 4.5 billion years ago. So we are really in presence of the very early material, and the composition that we will, for the moment we have not the precise composition yet, determine in a few weeks from now, will be fundamental to understand the process by which really the planets accreted. So everywhere we see that, terrace and boulders and small packed of grains, again, which have been transported at the surface here, not necessarily at the same point where they are located now, around because there is a very little gravity, so as soon as you have some ejection velocity, you can go anywhere around the comet. They are located here. So when we saw that first, there has been two possibilities. And some of the people said, okay, this is a double structure. So if it's a double structure, it might be the result of a collision between two bodies that early on collided and make the thing. So that's a possibility, and there are still people believing in that. And there might be some arguments in favor of that. They are trying to see if we have the same stratigraphy on the 2-1, and some people say, no, we don't have that, so they are different bodies. But more likely, it's exactly the opposite. We have a single body, and because of the outgassing, it is starting to be split into two and possibly more than that. And that's important. It would mean that essentially the outgassing will modify the number of bodies that we had very early on and have been responsible for essentially ejecting the material, even if it created a kilometer-sized body, into smaller body that afterwards could have implanted essentially the entire solar system with. So that's probably the case. And if that's the case, it means that unfortunately not this time, but maybe in a next occurrence, we might observe the disruption of this body into two or even more bodies in the future. Like that, you know, the more you add gas, the heavier the break between the two, what we call the neck here, will increase and evolve. So that's probably the case. Now, again, if you go to here, you see erosion on one side, deposition on many others, and this is essentially what you see all around this comet. You see always cliffs which are eroded with nothing in, and dust covering terrace everywhere else. And of course, I will go back to what we call this dust, but this is important. And these are two high resolution images in the places that we have selected as the landing sites. And this is the preferred landing site that you see here on the right. I will go back to that in a few seconds. And you see that essentially you have this mixture between those few cliffs and a lot of terrace. We have chosen this side because the cliffs are much less numerous on this one and much less steep, so in principle, wherever we land there, we should be safe. That what we call the backup side, and if I have time, I go back to that, but not necessarily. Again, it's essentially a flat surface covered with what we call dust. And the question is, okay, what the dust made of? And we start only now to have some hint of the composition of that. So a few things to remember here. First, it's very homogeneous. Wherever you look, essentially, with the resolution we have, for the composition resolution we have is only a few meters for the moment. When I say a few meters, it's already splendid that we have that capability. We are down to 7 meters now, and of course it will be better when we go closer, which is actually in 2 weeks from now. So we will have composition at a scale which is typically a few meters. And with that resolution, and until, of course, we land, and at the place we land, as you will see, we'll have much better resolution. But at least globally, we'll have a full coverage with a meter scale, and the composition is very, very homogeneous. There might be, from place to place, some departure, but now on, it might change in the future. When we have more outgassing, we might expose more bedrock and bed ice, I would say, in a sense. But for the moment, we don't see the ice, which is, when you think of that, it's not really surprising because of course, each time you go back close to the sun, the ice sublimates, and what remains is the most refractory that finally will make a crust. And this crust, and this is very important, is made essentially of organic material. And as you might remember, organic material are these pristine, complex organics which have been discovered for the first time during the 86 encounters flyby that Gerhart just alluded on, the two Vega and Giotto, demonstrate that if the comets are so dark, essentially, that's because the carbon essentially is not in the form of very small molecule like CO2 or CH4 that the people thought of before, but most of the carbon is in the form of refractory complex, maybe highly polymerized molecules. And why is it so important? It's that because these molecules have probably been formed during the collapse of the pre-solar nebula, out of which all the planets formed. But it's a very specific chemistry, because this chemistry, the chemistry that happened while this solar nebula collapsed, well, you had interaction between grains, gas, ions, and cosmic rays, and possibly the UV field of the early sun, if I have time to I can discuss that, because it might be that if this UV field was polarized at that point, it may have induced some extra non-chirality, and that might be the origin of what finally we had with life on Earth. So it's fundamental to realize that the comets have really sampled the early molecular cloud out of which all the system formed. And this chemistry was very specific, and these complex molecules are very refractory. It happened that they absorbed a lot of the light, so they are dark, and these molecules just trapped into the ice made the ice, which should be very bright, so dark. So these are essentially what is over the entire comet now. And we are very lucky that it's like that, because at least, because that's part of, it's not the only, but it's part of the major goal we have now with this Rosetta mission, is to identify these molecules, essentially to understand whether or not these molecules may have played a key role when they were trapped into the planetary oceans, together with the water that also went from the comet, actually. We wanted to know whether or not it could be the famous missing link for the emergence of life, but we still do not know the composition. And so we know that wherever we will land, we'll have access to these molecules. And that's a key part of the mission that we will try to get there. So that's essentially what I would like to say. We have a lot of organics everywhere. Virtis, for the first time, identified the organics, probably aromatic more than aliphatic, which is, again, even more important. We have also thermal properties. I have not really time to discuss that. Important thing, it's very, very porous, and the thermal inertia, as we say, is close to zero. It means that if it was ice, it would be thousands. If it was bedrock, it would be hundreds. It's only a few tens. So essentially, it's a very, very porous material that is everywhere at the surface, at least over a few millimeters deep, and possibly in some places over meters. So that's really, in a nutshell, what we think we have already understood of this comet, which is already by itself. We never get so much information on a comet as to that point now, although most of the information we get were by instruments that essentially made observation to help us finding a landing site. The real science is to happen now. So what do we expect now? First of all, what we measure, and then I will put that in the context of what we hope to learn. We have a lot of instruments on board, 10 I said, and so we have a lot of properties. I'm not going to go all through that, of course, but I have just separated that for you to realize that we would like to study the comet at all scales. First of all, we have ways to measure global properties of this comet, internal structures and the magnetic field. I just put here, you don't need to read that. What we want to know is we have the means for the first time to know whether or not there is structure within that. We have tomography by way that go through the comet from the lander to the orbiter, and we'll see whether or not we have some structures inside. Is this body differentiated or stratified? We have no idea, but that's fundamental because that will tell us something about the way these bodies accreted, and again, these body accreted exactly as the entire solar system accreted. So that's fundamental. The second, I have no time also, but that's fundamental. We have ways to measure the potential magnetization of the material there. We still do not know whether or not the early solar nebula was magnetized or not. It may have a lot of consequences on the way this nebula behaved afterwards. So we would like to know that. We have instruments to measure that, and that will be the very first time that we'll be able to measure both whether or not the material himself is magnetized or what is the influence of the comet on the solar magnetic field. Both of that will be observed. We will have a possibility to observe the comet at a regional scale. During the descent, we have a way to image by the zoom progressively that, but also when we land, we'll be able to measure the gas pressure and the variation of the gas pressure globally, the dust also, the environment, how the dust is behaving, and we'll make a 360 degrees panorama in stereoscopic ways just after landing. We have ways also to measure. And essentially, we'd like, for example, for the outgassing to know whether or not we have microjets here or there and how the comets behave when the activity starts. We have ways to measure the surface, at the surface scale now, the properties, mechanical properties, thermal properties, electrical properties. Thermal, for example, we have a way to measure the gradient of thermal, the temperature over the few 10 centimeters, and that's fundamental if you want to know what the energy outgassing, if I can say so, what the flux of energy, what the source of energy, how really it's distributed within the body themselves. We have the way to go now to sample, and that's really absolutely new, of course. We never had the capability to take samples, and we have a drill made by the Italian Space Agency, a drill that will go below the surface to take samples that will really pristine, with never possibility to go to the surface and have been potentially altered by the sun. So we go to this, and these samples will then be analyzed in sequence by 4 different instruments, as we would do in the lab, really, from the less to the more destructive ways, including mass spectrometry spectrometer at the end. What we want is really to have access to the isotopic composition, molecular mineralogical composition. We want to know what the material is made of. And I said something about the chirality. Again, that's for the first time it will be done in space. We want to know whether or not these molecules, which are here, has already the sort of fluctuation in non-chirality that might be used by living organism afterwards to go where we are, Lavoisier essentially, and we'll do microscopy. So all that is spread over our system, which is typically a cubic meter of instruments, of system and instruments. We have here the 10 instruments that I'm not going to really tell you much about. But again, you've got to realize that we want to operate far from the sun because we want to operate prior for the sun to modify the material. So it will be at 3 AU exactly in 6 weeks. So the temperature outside will be very, very low, depending of day and night shadow or not, but we might be below minus 100 degrees C. And for the first time, we'll be able to operate at that low temperatures. We have the camera, for example, are capable of making good pictures down to minus 150 degrees C. So we have been forced to develop, although it was in the 90s, develop at the limit of the performances of what was available at that time, instruments capable of doing that. But more than that, we have inside the body 40 kilograms of material, electronics essentially, that will have to warm up to something like minus 50 degrees because, of course, electronics cannot be much of them below that. And to do all that, to heat 40 degrees, 40 kilograms by maybe up to 100 degrees, plus 7 instruments, including 2 mass spectrometer, high voltage, whatever it is, a drill, supposed to drill, that's 30 centimeters is something as hard as concrete. To do all that, we have only a few watts, which is typically the bulb you are in your fridge, right? So we had been forced to really put at the limit all the expertise, the skill that European, essentially, industry had the capability to do with, and institutions. So why did we do that? And what is important is to realize that from the beginning, the decision of the SPC of ESA was 93, November 93, and we arrived 20 years later, typically. In between, the goals themselves are really changed because in 20 years, the view we have of the solar system and the reason why we do Rosetta has really changed in itself. That's really amazing. Just in a few words. What we profit by is that in these 20 years, it's really a true, what I call a revolution of our view of what the solar system looks like now. The word really that characterized what we have been doing when getting to all the planets during the past 20 years, that's really the diversity of what we see was absolutely non-expected. When you see really the studies that the space exploration has given us now, and of the role of the Earth essentially there, it's dramatic. And as you all, when we're in the process, we don't have the perspective to really take the magnitude of that. But really, frankly speaking, now we know that we come from a single nebula, and 4.5 billion years ago, we had all this diversity of bodies here, including, of course, that of the Earth. And the question is, of course, is what drives the evolution? What are the drivers of this evolution, and how to account for the fact that the Earth is so specific with the water table, the cloud cover, the atmosphere, whatever it is, which is discussed in these sort of sessions, of course. And it's not trivial to answer that, but to answer is essentially that there was what we call the initial condition. The origin is not a single point in the frame of cosmic evolution. What really drive this diversity here and drive the different evolution patterns is the fact that initial condition in the sequence of processes that spent over tens or even 100 million years, really, and not a single point. And now that we are really understood that, we want to really have access to all these processes. And what I want to emphasize here, that of course the processes, as processes are generic, of course, there is nothing special for the Earth, for Mars, and at the same point, there is nothing special for the solar system as compared to the other stellar system. The same sort of collision, the same sort of attraction, gravitational force, turbulent accretion, whatever, everything is generically the same. But the diversity of the form that each of these processes might take is such that when you put all that together, you have a huge diversity of evolutionary pathways. It's not that the Earth is different from the other planets, it's that each planet has its own way of evoluting. And now that we compare that, the solar system itself, with compared to the other solar systems, stellar system that we see, it's exactly the same. Migration, for example, everyone migrates, but the migration in our solar system is so specific that the question is, what is the likelihood, the probability that two places had the same sort of evolution. And what we want to really with Rosetta, and this is what I try to tell you now, is that with Rosetta, we have, of course, it will not answer all the questions, but it will be a key to try to solve these questions of how generic our evolution is with compared to the possibility that it's somewhere else. And in particular, that has to do with the life. The question, of course, is what are the conditions that enable life to start in our oceans, at least in the Earth's ocean? We don't even know whether it started elsewhere in the solar system. And we would like to know what is specific to our solar system with respect to, for example, when I said it's chemistry during the collapse of our protosolar nebula, it might be that another solar nebula collapsing will not make the same chemistry because we have to have a given density as a function of when the sun starts, and it might be entirely different. So we would like to know the processes by which really the complex molecule form have been then embedded in our inner solar system. So Rosetta essentially lay on two pillars. One, we want to understand the processes responsible for the diversity that we see now in the solar system. And second, we would like to know ingredients and processes that make life to emerge and then evolve, at least on the Earth. And the questions are, what are the ingredients? What are the process and the ingredients? Water, we know, when you drink water, you drink at least in a bottle of water two glasses of Comet. But the Comet in itself, okay, whether the water comes from a Comet and doesn't change the water, it's always H2O. What is important with the Comet that when you have the comet brought by the water brought by the comet, it also brings organics, and we would like to know what is embedded in the ices. And that's really what Rosetta, for the first time, will try to have access to. What is within the ice? And so that's what I put here. Exploring Comet is absolutely critical now in our complete scope of trying to understand what led to where we are here, the Earth as it is, and the solar system globally as respect to the other solar system. And again, we know the water were there. We don't know what the organics were. We need to know the processes by which it's created. We need to know what we call the activity, to which extent, because again, a comet as it is now is identical to the sort of input that we had early on in the solar system by similar bodies that went to feed the early accretion that fed finally Mars, Earth, Venus, and Mercury. So we want to know that, and Rosetta has embarked, as I said here, an unprecedented potential of discoveries because for the first time we land and analyze this material there. So this is what we want, processes, composition with a special emphasis on organics. So next step, of course, we want to land safely, and as we like also to say, not only NASA, failure is not an option. We've got to land in 6 weeks or half. So to start the last minutes of what I want to say, that, okay, that's where we were a few weeks ago. And I like this image is not only because it's made on, by our instruments on Philae, because for the first time we can see here the comet, our target, and the orbiter as it is now. Hopefully in a few weeks we'll see either only Rosetta from Rosetta or only the comet, and that's of course where we will be soon. So that's where we will land, and that's essentially the place here. We decided to land here, and I will say a few words there. So that's where I put the star, the red star here, and for you to realize where it is, I put here a green big structure just for you to recognize where it is. So the green, the big structure is in here, and you see where, so if you want to know where we will be located, it's on the star here. When I like to show that very close by we have a structure that is really a heart, so it's easy to know where we will be. It's close to the heart. And this is what we call not the landing ellipse, but circle at that point, because we don't really know the form of the ellipse. It's rather big. It's 1 kilometer almost in diameter, so it's rather big. And this is where we will land, in principle, within this circle. And just for you to have an idea of the difficulties here, at the same scale, you have here in colors the distribution of slopes. And on the right, you can see that blue is 0 and red is up to 60 degrees. Normally, we would not survive if the slopes where we land is more than 30, 40 degrees. So typically, we have to be everywhere about, except in the red parts. So we have a few. It's still risky. We have a still, if we are unlucky, we can land on the red spot, but we hope that everywhere in that site we will have the possibility to land safely. So that's where we are, but we might be in that sort of configuration, and that's an artist's view made in the US, of course, and well, they say, well, we might go on a cliff. And actually, there are cliffs. That's a splendid image just taken a few weeks ago. But we have chosen a rather flat surface, and there are movies when you see that rotating, but at least what I want to tell you that, yes, it's rather flat. And so that's, as the Beatles say, all we need is that. So this is what we need, and we have it. So normally, that's a good site. I would like to finish saying, well, it's absolutely amazing that thanks to our space agencies, ESA first, and then DLR, CNES, ASI, and many others, actually, that are not listed here, all the institutes, that we are in a situation where the dream to land on the comet, to understand really what the material out of which everything started, we have this possibility. It's already an enormous success to be able to rendezvous with that body, to see a comet from a few tens of kilometers, that no one ever did that. But of course, if it works, we will land, and that will be a truly historical venture. So if you are willing to be with us, just join. We'll be at ESOC, but as I said, reservations are required. I think it's already sort of overbooked, but you can still try. Thank you.
Thank you, Gerhard. Thank you, Jean-Pierre. You have just seen pictures that nobody out of the inner team has seen before. You have been exposed to results that has nobody heard before outside the real close circle of researchers. I think this is quite an event. And by the way, if you want to learn how to fly a spacecraft around a comet, how to dance about an object nearly 500 million kilometers away from the Earth, and how to land on a comet, then please note that on Friday we have a late-breaking news where Andrea Accomazzo, the flight director at ESOC, and Stefan Lunametz, the Philae project manager, will be available and tell you how to do all this. So we have time for maybe one or two questions. There are microphones up here in the aisles, left and right. So if there is a question from your side, please, the speakers are still here. Ask your question. Can I see if there's anybody? Yeah, can you stand up and use one of the microphones here in the center aisle? Here. Sorry.
Yeah, thank you very much for this absolutely outstanding and brilliant expose about what's going on with Rosetta. For those who won't be in the room or in the city Friday, could you tell us more about the descent process? Because we've read that there is there's an orbit around the comet, and the altitude of the orbit is decreasing progressively. So can you explain what will be the timing and the schedule for the decreasing of the altitude and the final steps to land, and from which altitude, and how long it will take to deorbit to the landing site?
Okay. You want to answer, Andrea?
Yeah, come on. This is the man who will actually be doing it.
Okay, thanks. Thanks a lot. So a couple of details on the landing. The strategy we have designed for this specific landing site and with this type of comet is slightly different from what we have conceived a few years ago in the past years. We're actually going to be in a 30-kilometer circular orbit just before the separation from the lander. And we will separate the lander when flying towards the comet at an altitude of, roughly speaking, 22 kilometers, and the descent will take 7 hours. So the lander will go down, fall very, very slowly onto the surface of the comet, take 7 hours to go down. So this is more or less the timing.
Sounds easy, doesn't it? Thank you, Andrea. Thank you, Andrea Comazzo. One more question. Yes, please.
So I know it's very difficult, and congratulations so far from the Jet Propulsion Lab and all those of us in the NASA family. Can you tell us roughly how many people are on the operations team for both Rosetta and for the lander? I'm sorry.
Well, at the control center where we conduct operations, we have equivalent of 30 people. Number of people involved are more, but definitely there are people that are not working 100% on the project. Then we have another 30 people taking care of coordinating the scientific observations. These are located in another ISA center in Madrid, in Spain. And plus you have all the scientific instruments. There it's a bit difficult, but if you count, we have in the order of 20 instruments on board, 10 on the lander and 10 on board the orbiter. Then you can easily go above 100 people involved in the project for sure. But this is currently what we have.
So 30 and 30 and then another roughly 100
yes,
associated
yes.
with the instruments.
In the order of 150 people, I would imagine.
Yeah. Okay, thank you very much.
Maybe you should stay up here.
Yeah, okay,
Let's. One more question we can take, preferably to the scientists. All the questions have been cleared. Oh, there's just
one question. It seems that there is a lot of dust on the surface. Can this perturbate philae?
Okay, first of all, there is a semantic problem. We call that dust essentially because it looks powder, but again, it might be organic grains essentially. So it's in between molecules and grain. No, I mean, to land on like a regolith would not be a problem in itself. The problem is we don't know the thickness and we don't know what is below that. So again, the global density is very low, 0.5, but what is important is the local density where we land. And we hope that this dust will accumulate into layers which will be sufficient to dump the system. But we arrive at something like 1 meter per second, so we have to be dumped, and so it has to be sort of rigid, that's true. So the real problem is, okay, what is below this dust and not the dust in itself. So if it's like a normal regolith on an asteroid or anybody, we are fine. If it's very porous inside, like dark ice, which might break under, of course, we're in a bad situation, but it's very unlucky.
Can I just make a remark to this? We have always the understanding that it could be regolith or something, but you have to see that most of the material has been there for a couple of billion years. And we have done experiments in the past and just to see, because you could have sintering processes. So even if it's low density and high porosity, you might have, so to say, a certain strength of that material. And this is something we have to learn as soon as the lander is there. So there might be regolith, but it could also be that it looks like it's regolith, but there is some strength between the grains there. And this is one of the big questions we have. If during the comets are around there for 4.6 billion years, so you could have what we have on Earth as well, sintering processes, they have long time. And then you get a certain strength, and therefore would be, you could expect that the surface is, it's not really only dust grains lying around.
I think with this, I'm sorry we have already overused our time here, and I see after a long day you're getting tired, but I think we should give a big hand to our 3 speakers here. And there's a special gift that we are going to give to our speakers. Guy Liberté, as you know, has been a tourist on the International Space Station, and he condensed all his impressions into a wonderful book, which is here, and we will hand out one of these books to each of our now 3 speakers. And with this, I would like to extend my thanks to you to this excellent presentation, and I wish you a good evening. Thank you very much.